English.
Okay, yeah, that'd be great. Thank
you.
you.
See, it's not about, you know, studying algebra is not for people like you. Is not really, you know, associated with, you know, formal approach, which have, you know, to get familiar with this, operation like multiplication, for how to find inverse. The more important thing is the idea. Okay. For example, when we say multiplication of two matrices, so what is the idea of multiplication of two idea in terms of our previous description?
Yeah, a transformation on a sort of state of the system followed by another transformation.
Yeah.
So,
in other words, you want to combine the two transformations together. Okay, you want to join the two steps as one. Okay, that is the idea behind a multiplication of two vectors. Simple, right? Similarly, how about we move backward? What does it mean when you're doing the multiplication of matrix and a vector? What does that mean?
Well, I suppose it's just a single transformation. So
yes, that's right.
Yeah, so it's I've it's not composition.
It's just transformation. You are right. It's transformation. So let's go to whiteboard. Yes, it's just transformation. It's transformation allows you to write that transformation mathematically. Okay. For example, say someone will see you this. Oh, today looks good. There must be some comparison, right? It's compared with yesterday. There's some transformation, but unfortunately, in this practice term, they cannot find the metrics to describe this transformation. Do you know what I mean?
Yes.
Okay, of course. In the linear algebra, for any phenomena, we can, in principle, to describe this transformation.
Yeah.
If the step of change is small, then we can always use metrics to describe it. Okay, without consider say any complicated detail. So so that's how we use this multiplication. So whether you know, the reason I write down the formula last time is that to tell you that sometimes the operation can be crystallized into very simple, compact mathematical form, and in which you just count. Okay, for example, say if you forget the multiplication, you just count. Okay, so it doesn't matter. I can be people like you, and you don't have, you know, like the regular students who can do practice 1 hour a day. You can't, right? But essentially, you catch the idea. Okay, big idea, big data, big data, big idea. So I think that's we're focused on this. So today we'll give you something new idea. It's called the representation of vector. So every day, every time I give a big ideas. Okay, representation of a vector. Actually, we have encountered these issues before. Just different name has been used. Perhaps a little bit of generalization will be made in this case. Okay. So a vector, for example, A, we have used A. In general, we can say that A can be represented by a set of unit vector, as we did before. If you just go to 2 by 2, that would be simple, right? That would be equal to AX, I, plus a y components j. So this is how we write the representation in the 2 dimension. So you can either use this linear equation form, or you can use the matrix, Coulomb matrix. Okay. So this is the simplest example. So this is good example. Okay. By the way, when we say we study the vector, it mathematically is just arrow. Do you agree? It's mathematically is just arrow. Can we draw here? The mathematically just arrow somewhere like this one, and which can be the direction and length can really describe the position of particular point relative to the origin. This particular point called P relative to the origin, right?
Yes.
So of course we don't have to. in the absence of the choose the coordinates, we just see the arrow. We see the length, and can we just call this A? We know the length and we know the direction graphically. That's all.
Yep.
Now these vectors can be used to just describe many things. Among other thing is a vector could be represent a state. Okay, so the vector could be a state. Okay, or a situation or market situation. I just try to draw some idea from yours.
Yeah.
Okay, market.
Sure.
Okay, market situation, a performance. Okay. So the vector is, in general, we can. That's why we study linear algebra. You see, we're not just studying linear algebra for the argument for the sake of argument doing math. We actually apply this idea to relate it to solve the practical problem. So the vector can be, in this case, for example, the state of the motion. So for example, the state of the motion. So state of motion can be described by, say the velocity in this case, right? And the position as well. How to describe market situation? If this A is market situation, what parameter would you put there?
I'm trying to think macroeconomically.
DJ index.
Well, actually, there's a concept in macroeconomics which they call the velocity of money.
The flow. The velocity of money or flow is a flow of
velocity. So referring to the
flow, right? Capital flow.
Yeah, exactly. Yeah.
Oh, okay. That's good.
Yeah.
That's good.
Yeah.
So you can put all numbers is four numbers. So you forget about this one of representation. So this is another representation. Okay. And how to describe what you call volatility? How to explain volatility? Any
volatility? Yeah, that would be. That would be.
Volatility or another because anything called volatility at all? Volatility? No?
Not volatility.
Not volatility. Do you put a number to describe the market situation? No.
Yeah, it would be sigma.
Oh, so, yeah. They use a sigma. You use sigma, right?
Sigma.
Oh, good. So you have a lot of things.
Yeah.
You use a vortex. This mathematics is fluent. Perhaps you can introduce some vortex to describe money flow, because sometimes you got a turbulence, so you can hardly predict your return.
Maybe in a couple of years, I might be able to do that.
I'm just joking, because so basically you see the representation everywhere when you describe the same situation, at least in the news. Okay, they will give you interest rate. Anything else?
Yep.
The benchmark index, right?
Yes.
Anything else? Anything else?
Yeah.
Three popular consumer index.
Consumer confidence, business confidence. Market volatility. Probably.
Can you teach me the word market volatility? How to write that word?
VOLATIL.
Oh, this one.
Yeah.
I use it similar to this one.
Yeah, exactly.
Oh, I write down here a volatility. Oh, this is not T.
Yeah. Yeah, which TILITY.
TILITY. Wow.
Yeah.
Tivity or tivity?
Tility.
Tility. Wow, that's tivity. Well, in physics, there are many tivity, but this is tinity, right? Is that right?
Yeah. No, okay. They changed up. And it's just standard deviation of returns.
Okay.
That's it. Yeah.
Is that the state or process? This parameter is a state or process?
That would be it's hard. It's it's both, because it would be a.
It's a rate. It is a rate. It's a rate, or.
I'm trying to think. It would be over a specified time horizon, so it would be, say,
given time period. Yeah.
Given a volatility over the last month.
Oh, I see.
You would look at the variance of returns. Yeah.
Yeah. But anyway, that is, you see, that's how the vector can be used to describe the situation like that, even beyond the mathematics, beyond physics, right?
Yes.
But when we represent that, we just return to this formula. So basically here, when we write this ax and ay, we imply we have chosen particular coordinates. In this case, this one. So the vector, if you want to describe vector in the components form, you must specify the basis. Yeah. So that's important concept here. We're trying to generalize this from this 2D. So in this case, we may just probably just encounter in this case, just x and y. Okay. So we actually, when we say that, we actually, in this case, we must specify, we choose two vectors, which is a unit vector to represent the direction of these two axes, right? So when we write this form, we will write these abstract vectors, then we imply that we actually have to choose in these two reference or basis called the basis. Or we say base, okay, so the base, so basically this is a set. So what is a base? So that's basically I write down here. So what is a base or basis? Base is just a set, a group of elements, a set of orthogonal unit vectors. Okay. So sometimes call the basis, some call the basis. But anyway, so this is important concept. When you want to represent a vector, you have to choose a specific basis. And in this case, in this 2D, in this case, the two bases here are the I and J. So therefore, in this case, we can use the projection to represent these particular vectors. So this is AX and this AY. But the representation are not unique, okay? In general, you can use arbitrary, the choice arbitrary. Okay? No one can stop you to choose this particular coordinate. Or you perhaps, if you wish, you can choose your x. I use different color. You can choose your x-axis along different direction. So this is your x now. No one can stop you to choose different x-axis. Even this case, you see.
Right. Okay.
You see. So that's why let's go to the next page. We will just probably write down this. So in general, that's notation. So any vectors. So in general, okay. Every time I give you some important key ideas, okay. So then you can repeatedly use this idea to see. So in general, any vectors A can be written as the sum, okay, of, can you put the coefficient here? If we use can we just use the, I don't want to use this A, which coefficient, can we use use the proper names? Can we use alpha I? This is ui.
Yep.
Okay, ui, and I equal to 1 to n. So n is a dimension. Okay. So that is general. This is general form of a representation. If you expand that, that would become alpha 1, u1 plus alpha 2, u2 plus alpha 3, U3. So this is very general form. So that's alpha n and un.
Yeah.
So where the u is a unit vector. Okay. So unit vector means that unity vector means that another way, very same vectors A can also written as in the different bases. Say, can we call the beta I, vi, I equal to 1 from I to n. Similarly, you can expand that alpha I, ui, so another uv. Okay, so v1 plus beta 2, v2, and so on until you get beta n, vn. You see?
Yes.
And these can be written as a matrix form. So that first one can be written as alpha 1, alpha 2, until alpha n. You see that? And obviously, these numbers are different. Can you see? Beta 1, beta 2, and beta n.
It reminds me of regression.
Yep.
Yeah.
So obviously, this number is dependent on the choice of the unit vector. We all use the base, okay? Now, when we say it's orthogonal, we can use our knowledge of the dot product to define this. So basically, in this case, for example, for the first base, ui, dot product. Do you still remember the dot product?
Yes.
And the uj, they all have two choice. Okay, there are two choice. So basically, we will use this notation. I just use the simple notation. They have either 1 or 0. When equal to 1 is when I equal to j. You see, if they're the same, okay, the product will be just exactly 1 unit. But if the I is not equal to j, it's 0.
Yes.
So eventually we will use this simpler notation, more compact notation to represent this orthogonal property. So I, j were equal to delta ij. The same thing. So we just redefine as I delta ij as equal to 0, 1 or 0, 1 or 0. If I equal to j, and if I not equal to j. The same thing.
Okay.
And similarly, we can argue that this is a V. This is another set of bases. I dot product j, not v. Sorry, this is a where is vj or equal to delta ij or equal to 1 or 0, depend. If I equal to j and if I is not equal to j.
Yes.
So this is what I mean orthogonal means. This set is orthogonal. Orthogonal. Okay. Now, if we just go to very simple example, if n equal to 2, we return to the 2D. Okay. In the 2D, we just return to our x, y. So in this case, u1 just equal to I, can you see? And we use I as the directional vector of x-axis. u2 were equal to j.
Yes.
So if you draw the picture, you will see that indeed they are perpendicular. Can you see if you just draw the? So this is I can draw this diagram here. This diagram, okay. So in this case, the I and the j, I would prefer to use the u and u1 and u2 instead of ij. Okay. So if you write this way, we got this x, y, And this unity vector, the unity vector here will be our U1. And another is U2. We always choose a positive direction as a direction of unity vector.
Yep.
So this is 0. So that's 1. Is also the 1. And that will be our U1. That will be U2. Obviously, U1 and U2 are perpendicular to each other. Can you see that? This 90 degree?
Yep.
90 degree. So when we say this is orthogonal, which means the two vectors are perpendicular.
Okay.
Must be perpendicular. So that is how we describe the dot product here. So therefore, U1 dot product U2 in this case is always equal to 0. They must be always equal to 0. Okay.
No projection.
No projection. Okay.
Okay.
So let's go to so that is general form. Okay, a little bit abstract, but perhaps we're just continue this example 1. Can we just consider example 2? Let's just consider the same example this time. I will just draw some example 2. This time I will discuss this situation. This is very here we have two sets of the coordinate or two sets of bases. Okay, so one is this one, another is a green. I use the green colors. Another is a green. In this case, they are overlapped. Okay, it's hard to draw the overlap. I just draw them very close. Implies they are actually overlap. In this case. Or perhaps what I do, I draw this. Yes, I drew this overlap because we're going to draw the graph here. So this basis one. So it's green. There are two bases, a pair of bases. So we just consider a pair of bases, different bases. So one is a green. One is a green, one is chemical, two bases. One is in this two-dimensional. One is U1 and U2. Another is V1 and V2. They are all unity vectors. Okay, they are all unity vectors. Let's just finish this diagram here. So this is X, this is Y, and this is X prime. So this is another one is different direction. Let's just change that a little bit. Yeah, I will change the direction of the blue one to other side. So this is blue one. This is X. This is X, and this is Y. Okay. Now then we consider the vector here, a vector which is somewhere like this one. This is a vector. Let's say it's to this one here. Let's say 2, 1. Just write a larger one. 3, 2. So this vector is roughly 3, 2. So this is a 1. Just draw that properly. 3 unit. This is 2 unit. Yes, 2 unit. So this is I think I will draw it separately. Doesn't matter. We will draw it like this one first. So this vector and this coordinate on this coordinate here is 3. So 1, 2, 3 is 0. 1, 2, right?
Mm-hmm.
Now, how to represent the base in this case?
Right. Well,
Can we call this is this coordinate is 3, 1, 3, 2, right? 3, 2.
Yep. Yes. But also, I'm trying to figure it out.
Can we call this vector A? This A. So the vector A can be written as in the first set basis is the first base, the second base can be written as components, right? So in this case is 3 U1 plus 2 U2.
Yes.
Okay. How about this very same vector in another base in the V?
Well, I suppose there's a 90-degree rotation. So would
yeah,
it be...
90-degree rotation. Yes. So this would be the 1. So this would be relative speaking. This would be positive. X is a positive, right?
Yes. Yep. So it'll be...
Would be 2. It would be 2.
Yes.
Yeah.
2, -3.
-3. That's right. Good. So they got 2 and -3. So the number change because of we choose different bases. So this is V1 and that's V2. Okay. So that is the example how do we represent the same vector by using different bases. But these numbers are related. Okay. For example, how do we represent U? Okay, this example, they just say representation. Okay, actually, I just continue representation. Another idea, representation of UI. Sorry, not the VI. Sorry, VI and V2 in the set, in the representation, in term of UI, U1, and U2. For example, how to write UV1 in terms of the 2 basic vectors? Because this is also the vector. You agree?
Right. So would it be correct to say you can change between the two by applying the matrix which represents a 90-degree?
Yes, that's right. That's
summation.
right. Yes.
Yeah.
So in this case, the V1 is aligned with the y-axis.
Yes.
So if I use column vectors, how can we write this vector, unity vector V? That is V. I should draw this clearly. So this is our V. That's V1. This is V1, and this is V2. So we find V2.
Ah, yes. So
in the older frame, in the unit, in the U1 and U2.
Oh, right. Okay. So it's -1, 0 and 1, 0.
Now, in the case of V1 or V2.
Oh, sorry. V1.
Yeah.
Is that going vertically? That's going to be in terms of U. Yeah, that's going to be 0, 1. Oh no, 1.
Yeah, 0, 1. You're right. 0, 1. Yeah.
0,
1. Yeah, 0, 1. Yeah. How about V2?
-1, 0.
Yes, that's right. -1, 0. So you can see we can not only we can represent any vector, but also by choosing a particular basis, we can also represent a unit vector of other bases. That is idea here.
Mm-hmm.
Okay.
Yes.
So this just tell you that we can arbitrarily choose any direction as our basis.
Mm-hmm.
Okay.
Okay.
So what is the relation between these two? If we just substitute this one, so what would be the components in the second basis? So what would be in this case? What would be the coordinate in the second basis?
In terms of V.
In terms of U.
Oh, in terms of U.
Yeah.
Not in terms of U. Is it not just 3, 2? Or no? I'm lost.
Oh, sorry. In terms of sorry, my fault. In terms of the second basis.
Right. So 2, the 2, -3 in the vector, right?
So can we just substitute this into this equation? So can we this called equation 1, equation 2?
Oh,
okay. So
okay.
the equation is 3 and 4. So if we just substitute and 3 and 4 into that equation 2, so we got vectors.
Yes. Yeah. 0, 2
multiply.
0.
That is 0, 1. You see.
Yep.
Plus. And we put the coefficient -3 here.
Mm-hmm.
-1 and 1.
Mm-hmm. So 0, 2 plus 3, 1.
Yeah.
Will be the two new vectors.
So that will be 2 here and a positive 3. Can you see?
Yes. Yes. Yes, and it takes you back. Okay.
It takes you back.
Yep. Sure.
So you can see if you can renate, in this case, it's very simple. It's just 90-degree rotation, right? But in general, you should be able to transform you can prove that they are equivalent in terms of description, in terms of representation of the vectors. Okay.
Right, and the matrix 0, 1, -1, 0 will apply a 90-degree rotation to any vector.
Any vector, yes, right.
Yeah. Okay.
So therefore, you can you can build the transformation based on these two matrices to finish to complete to obtain the same to actually transform the representation from one to another. If we know that if we know this representation of the new basis.
Mm-hmm. I see. Okay. Okay.
Yeah, I think I probably need a bit. I just go to some detail here, perhaps.
What would be a sort of practical instance in which you would not use sort of standard basis, I guess? Like what? I understand that abstractly, yes, if you wish, you can represent things in any basis, but why would you stray from the standard sort of 1, 0, 0,
well, yes,
1?
as I say, there's no standard one. There's arbitrary one. There's just convention. For example, we choose a particular coordinate so that you can see that we can only see the commonly used basis. Okay. The reason is that you see the reason we do this transformation is that can we just obviously, you can make the argument. You can build the matrix here. Can I just remind you? So if you build a transformation matrix in this case, let me try. If you just make a transformation matrix, can you T this transformation? And by building this 2 by 2, by using the representation of this new basis written as 0, 1, can you see 0, 1, negative 1, and 0, 2. So how did I build this matrix? I use these two. So basically what I do is I just highlight this operation. So this column is made by this one, can you see? And the other column, so this column is made by this one. So this is how to obtain the transformation matrix if you know the relation between the two bases. Okay. So then what we can do, we can this is actually the same operation here. So basically what we can do here, we can just multiply the matrix. We can multiply the matrix. Now originally is can we say is 2, 3, 2, 3. Can you finish this product of the two matrices?
Yes. So it's the vector 0, 1 multiplied by 3. So 0, 3 plus plus negative 2, 0.
So that's 0 multiplies 3. So 0 multiplies 3 plus, right?
Yeah.
Negative 1 multiplied 2.
Yep.
Okay. And this is 1 multiplies 3 and plus 0 multiplied 2. So you got negative 2.
So we end up with
and positive 3.
Yes. So
what does that mean?
That means that took us to the new basis because so that transformation took us from one basis to another. Oh, sorry, it recast that vector in the new basis.
Yeah, I noticed we have something wrong with the sign. Here it would appear that we just, this is the opposite from our notation, can you see? We got a positive, we got a positive, they got a negative here, but they got a positive, negative here. Something's wrong. Can we find it out?
Yes, 0, 1, 3, 0, 3 plus negative 2, 0. What happened there? 0, 1, negative 1, 0.
That's right.
3, 2.
Yeah, we're right. We say negative 1 multiply negative 2, yes.
Yeah.
Positive 1 multiplies 3.
Yes.
Yes, that's how we do it. Something interesting. How can we get the sign incorrect?
Yes. Maybe the unit vectors incorrect? No. 0, 1. No, the first unit vector should be Oh no. Is it 1, 0? Negative? I don't know.
I think realize that the matrix we built here is actually should be used as a transformation from old one to new one to old. But we are trying to work out the transformation from old to new. So we have probably used the inverse here. Let's try this. Let's try this, okay? If we use inverse, what would happen? Can we find some space? Next page. And just 0, 1. So we got this transformation is at 1, 0, right? 1, 0, and negative 1. Sorry. 0, 1, sorry, negative 0, 1. 0, 1, 1, negative 1, 0, okay? Can we work out the inverse of this one?
To take us back instead of another transformation.
Yeah, it's just it's called inverse. So we'll do some inverse exercise. Inverse matrix.
Yes.
How to find the inverse?
This is what I struggle with.
Well,
this is
by definition, what is inverse?
It will take us back to identity.
Yes, that's right. By definition, we use a definition.
Mm-hmm. So
T and T inverse were equal to unit vectors, right?
Yes.
Okay, so here is H. Can we just assume that, we just assuming the inverse is equal to A, B, C, D, 4 elements.
Mm-hmm.
Okay. So we got a T here. So therefore, because where I is a unit vector, 1, 1. Okay.
Mm-hmm.
So then this plugs this into this equation. So we have the first term is 0, 0, 1, -1. Okay.
Mm-hmm. Second
term is our A, B, C, D.
Yes.
And the right-hand side is unit vector, identity vector, right? Identity vector. Mm-hmm. I should call it identity vector as 1, 1, 0, 0.
Mm-hmm.
Okay. Here's again an opportunity for you to finish this product of 2 vectors.
Yes, in reverse.
No, this is just a product no.
Oh.
Yeah. So basically, we need to find 0, -1. Yeah. 1, 0. Multiply A, B, C, D. So that would be another vectors, 4 by 4, 2 by 2, right?
Yes. A, I, K, B, K, J.
0 multiplies A plus -1 multiplies C.
Yes.
Okay. That's the first element. That's the first element. How about second element?
Second element is our
0 multiply A, and even our B, right? 0 multiply B, 0 multiply B, and -1 multiply D.
Yes.
That's second element. Okay. How about third one? How about this third one?
Okay, so that's
1 multiply A.
I've been working it out in terms of IJs.
Okay.
Yes, 1A.
And 0B, right? Plus 0B.
Yes. Yes.
So last one is 1 multiply B, 1 multiply B, plus 0 plus D, multiply D. Okay. Okay. Simple. So what is the result?
Okay, 0 by A is
0.
Is going to be 0 plus, so it's negative 1 C.
Negative C. That's next first element. Okay.
Negative C. Yep. And then negative D.
Negative D. Good.
And then A.
A, just A. Yeah.
And then just B.
That's B. Good. So this is our left-hand side. This is a left-hand side equal to this number. So they must be equal to right-hand side. So what we have obtained is negative C, negative D, that is A, B, must be equal to this identity vector. So identity matrix. So what we can say about these four numbers? What is A?
A is going to be.
You compare with this one.
Oh yeah, sorry. A is going to be 0.
Good. How about B?
B is going to be.
It is B.
1. Yes.
Yep. How about C?
C is going to be -1.
-1. Good. How about D?
And 0 again.
Yeah, D equal to 0. So in this way, we can obtain, in this way, we can find, so we substitute that one, into that one, so we can obtain the inverse. We're equal to A is 0, D is 0, okay? B is 1, C is -1.
I see.
Okay, we are getting there. So if you back to, if we repeat our calculation to the transformation, so we're trying to transform the vector in the original basis into the new one. The old one is a 3, 2. Okay, so we can multiply this. Yeah, that should give a correct answer. So if we, can you follow me? So
yep.
So therefore, if we use a T inverse, multiply these 3, 2. Okay. So another exercise. Let's just go to next page. Okay. We got the vector product here. So we just continue here. That's from 0, -1, 1, 0. Is that right?
I think so.
Multiply 3, 2.
Yeah. So
let's double check that. Yes. 0, -1, 1, 0. Okay. Let's see if this is correct answer.
Which is going. The first vector will be 0, -3.
Yeah. 0 multiply 3. Yeah.
Yeah. Sorry, I was going down. Yep. 0.
And 1
plus
1 multiply 2. Can you see?
2. Yep.
Multiply 2. How about this? How about this element? -1.
3, -1. Yep.
Multiply 3 plus
0
plus
-2. 0, 2. Yeah.
Okay, this time should be all right.
Yeah. So we get 2,
-3.
-3.
Yeah, that's correct. Let's check.
Yeah.
Okay. Indeed, this is -3. Can you see?
Yes.
This is -3 and +2, right?
I see.
So you can see the number change, but the vector remains the same. We didn't touch the vector. We just choose the coordinate. Okay, to answer your question, your curiosity, why we make this trouble to find this, a different representation? Well, there's a practical benefit here. You see, if you accidentally choose this one, let's just go to explain the reason. So this just stay with this vector. We just draw this vector again. So vector A here. Now in this time, if we choose X axis, so this is original axis. I use different color. So this is original axis. Do you agree? So therefore, you got a projection. You got a projection, right? All the time, non-zero.
Yep.
However, if you put the x just parallel to this these vectors, what would happen?
You lose a dimension. So no, yeah.
So the y is still there. So y, so remember, they must be keep orthogonal. See, the y will be here now. Can you see?
Right, but it can be described entirely using x.
You can use the you can use the basis vector. So this x, can you see? So this y. Can we call this unit? So this is unit. Okay. Yeah, that's why we take this trouble. Can we call this Can we call this choice is w? Okay. This base is w.
Okay.
So we just write this w1 and w2. This is our. Can we just? This is a second choice. This is another choice. This is a different x-axis, but A remains the same. So in this particular case, what would be the representation of the A-axis, A vector?
It would just be, I don't know, say 3, 0 or
yes, that's right.
3.
Not 3. It's a magnitude.
Oh, sorry.
Magnitude,
AX.
Can we just work out its magnitude first? So from this first example, we can say that the magnitude of x, the magnitude of the A vector, we just follow the Pythagoras theorem, can you see? Okay. So in this case, what is A? So A will equal to, which means I use it to represent the magnitude. Okay. That's just equal to 3 squared plus 2 squared, Pythagoras theorem.
Yes, yes.
Okay. It's just numbers, you agree? Just numbers.
Yep.
So what is number? 9 plus 4. 9 plus 4.
Yep, so 13.
13, yes, square root of 13. It's just numbers, all right?
Yep.
So in this particular case, in this particular choice, we end up with a square root of 13, square root of 13, and 0.
Yes.
In other words, if you rewrite that the linear equation, that became square root 13 multiply W. 1 and 0 multiply W2.
I see.
Okay.
Yeah.
So remember, these are transformation. These are transformation. Okay. These are transformation from old to new. Not not T, this is T, so where this one, this transformation, can we just use this, I just use the T inverse, okay, T inverse equal to 0, -1, 1, 0. Of course, this is general, this is for particular example. So in general, in this case, if you just rotate this one, so this is let's just do this one. This is original one. So this is original x. This is original x. Okay. So basically, we want to transform this representation in old x into the new one. So basically, we can just write that. Can we just simply write as I think I just write this. So basically, so this is the vector. So this vector. So in this case, we count that A, when we just multiply this A. Normally, we use a matrix here. We use a matrix here. They will give us different vectors in general. But in this case, particular case, A is our, in this case, W is one of our unit vectors. In other words, we know that A will equal to square root, so A will equal to a square root. So in this case, in this particular representation, this particular representation, A is just a multiple of one of the unit vector, W1, W1, not W2, W1. So therefore, if this transformation is M, which is different from our previous one, because we choose different sets, okay, set. So therefore, in this case, we will end up with equal to M multiply the square root of 3 and W1.
Yes.
So what does that mean? So you end up with that the vector, the transformation just is a scaling, is issue just a scaling this vector.
Yeah.
So this particular transformation will bring the V into the particular form.
But are you talking about, is M to transform back to, is M a 45-degree rotation back to what you just drew?
Well, it's not necessarily 45 degrees. The point is that the new x-axis will be parallel to this vector A. This is arbitrary vector, right? But in this particular choice or in this particular representation, A is just a multiple of one of its unit vector.
Yes.
That is the point.
Yeah.
That is the point. So therefore, the transformation can be described as the A, in this case, if we just, how to say, if we multiply this one, that will equal to square root 3. We put this number here, okay? And then because this number doesn't change, okay? Number is not a vector. Number, we can put this number in front. We end up with this mathematical form here.
I understand. Okay, so that yes, the matrix is transforming, but it's not shifting, it's just scaling.
It's just scaling. So in this case, you're just scaling, okay? So just scaling. So therefore, that is why we choose different bases in order to find the particular representation. The transformation is so simple. It just involves the scaling. No rotation. No rotation.
Yes. No rotation.
That is the point.
Okay. I get it. Yep.
Yes. Okay. So in general, you see, we have taught this is general. So in general case, if you arbitrarily choose any basis, we end up with this one. Okay, different vectors. Okay. But in the special case, we will end up with matrix multiply the vectors. Say they multiply the W1 will equal to a number. Multiple W1 in this case.
Yes.
Now, here I want to draw your attention. Obviously, you have learned this before. So this number is called eigenvalue. You see that? And this is called eigenvector. So this W is called the one of the correspond to this particular eigenvalue is called the eigenvector.
See.
Can you see that the concepts are connected now?
Yes. I get it. Right.
Okay.
So it's like a simpler way to describe the transformation.
Well, we are looking for something very representation must have some representation is unique, very useful. Yeah, I wouldn't call it standard, but it's just called eigen. It's just representation, and it takes some time. Next time we'll introduce another idea in which in this case, the matrix will become diagonal. In this particular case, and M will become diagonal. So that's good news, right? So if you say this is a 3, 1, -2, and say it's 4, okay? And then if you go to their own representation, so each matrix imply they have its own representation. In its own representation, this just convert into two numbers. In this case, say it's 5, -2, 0, 0, you see? So this in the representation of U, UI. This in the representation of WI.
I see.
All right.
I see.
This is the first time I'm trying to put all idea together now.
Okay, but that I mean, you've definitely answered my question as to why people change bases.
Yes, that's right.
It's to get better representation.
Yeah.
Easy to work with.
We can easily work out this so-called eigenvalue. So once we got this eigenvalue, and we next time we encounter the matrix vectors, we just multiply this value, positive, negative, or 0. Okay. So transformation become much easier.
How exciting.
Yeah. Yeah.
Cool.
Well,
Okay.
the central issue is to find the eigenvalue and eigenvector for many transformation vector, transformation matrix. Remember, that's all.
Okay. All right.
I will see you next time.
I look forward to it. Thank you very much.
Do you want
I'll
to
see you next week.
save everything. Save this.
I will. I will.
Okay.
Wait up.
Let's go to page 1. This one, page 1.
Yes. Sorry. Yep.
2.
Yep. Got that.
3.
Yes. Got that.
4. Yeah, got that. 4.
Got 4. Yep.
5. Yep.
Brilliant. Got it. Thank you very much.
Okay, I'll see you next time.
Okay, I look forward to it. Have a good day.
Okay, you too.
Goodbye.
Bye-bye.